Good afternoon to all of you, and we will have uh, slightly reschedule our talk, but today I will talk about Himalayan cryosphere under warm climate. So there are numerous ideas which have been used to understand how climate and cryosphere will interact and how we can predict what will be the fate of Himalayan cryosphere. Until now, we have extensively talked about the technique and methodology to understand the state of the cryosphere. That means how much is its extent, how much is its mass balance, what are the different methods to estimate mass balance or to estimate the glaciers, its volume, and numerous other parameters, how to delineate seasonal snow. So we have learned the methods, technique, and the state of the Himalayan cryosphere. Today we will talk about what are the different techniques which have been used by numerous people to understand the fate of cryosphere and what impact it will have on some of the sectors which is related there like water availability or availability of its impact on hydropower and on communities. We will try to address some of these issues. Not necessarily we have conclusion for that issue, but definitely you will get the direction to do the work, further work in this way. So we already see in this figure, which there are a couple of figures I will show you again. Essentially because it will give you understanding or it will bring you continuity to our thought, which we have done earlier. So we know that if you consider three basins which are relevant to the context of India, like Indus, Ganga, and Brahmaputra, we have approximately 3,236 gigaton glacier water store in this basin, and the highest one is in Indus Basin. More than half is in Indus Basin. Then certain amount, around 600 cubic kilometer in Ganga and around 897 in a Brahmaputra Basin. In addition to that, a seasonal snow cover is also a major component of Himalayan cryosphere. We have during winter time approximately 1.6 million square kilometer area, and that is the maximum area you can see during winter time, and it reduces almost 10% um, during summertime. So that is from 85% to 10% is a variation in snow cover. That means from winter to by the end of summer, um, the seasonal snow melts and produces significant of water into these three river system. In addition to that, we also know that there's a significant amount of you know dependency, and dependency as Indus Basin is much higher, essentially because the most of the precipitation received there in a monsoon time, not in monsoon time, in western disturbances, and in form of seasonal snow, and it has a large area under glacier. So because of that, this is concentration of or the snow and melt contribution is significantly higher in Indus Basin compared to the Ganga and Brahmaputra Basin, essentially because Ganga and Brahmaputra Basin receives a significant amount of precipitation during the monsoon time. We also know that Himalayan cryosphere or Himalayan region has is rising their temperature much more than global mean, or that matter a global mean or mean temperature rise of Indian peninsular part. So we know now that if you look into this figure from 1950s to 70s, the temperature was Himalaya was much lower, and as of now from the mid 80s, this is significantly higher than temperature into the overall India, suggesting that as we go higher into the atmosphere, either cooling effect or warming effect is much more higher than the mean effect which you see around mean sea level. In addition to that, there is also precipitation change, and we know that certain part of Himalaya, particularly western disturbances in this part, receives the more precipitation than normal. Certain regions uh, have slightly reduced precipitation, but there is also reduction in precipitation in northeast Himalayas. That is also we can see from this figure, which is done by IITM. So in addition to that, in Western Himalaya, where the precipitation has gone up slightly higher, there is also decrease in snowfall, but slightly increase in the rainfall, creating certain sort of anomalies. And as a result of that, most of the glaciers are losing mass quite significantly. And you can see for it last decade, almost 16% mass loss we can observe in Satluj, 17% in Bias, 10% in Chandra, and 8% in Alaknanda, and almost 6% in Bhagirathi. So there is a significant mass loss is taking place into the Himalayan glaciers and resulting it towards the significant amount of glacial retreat. So this figure we can see in a Pindari Glacier from 1936 to 2006, how glaciers have lost. So this is a Pindari Glacier, which are much bigger and healthy, and now that is only restricted into this part of the Himalayas, this part of the valley. So you can see here, this is the only valley, and this entire region has really vanished. So clearly suggesting that glaciers are retreating and losing mass, and we know that in an average, the glaciers are losing around 14 to 15% length every year, except in Karakoram. So we have an anomaly in Karakoram. So I think up to this point, we have discussed the issues, and I wanted to recollect you this issue. And we have discussed about the Karakoram anomaly in our previous lecture. So we will look into the data and try to understand what are the what is the fate and what really it suggests significantly. So first thing we must understand is I will try and discuss some of these ideas which is fairly old one, and then there's a significant change in the ideas that have taken place. So you should understand how this effect of climate change and Himalayan glaciers and what will the fate of Himalayan cryoshere is evolved over a period of time. So we will try and look into this in the simplest ideas, which was tried and published in year 2009. You can go and do the uh, you can download this paper and read it for more details. But I would like to give you some of the key ideas which were given in a 2009 paper. So at that time, the idea of climate models and other things were not clear. We will look into that in a subsequent slides. But right now, you see, what was thought was that what will happen to the runoff, which is a small glacier, small basin. You have already worked on those models. You have done the exercises, and I have given detailed talk about those models. So we will not go into the detail of that model, but we will see now how same model can be used to estimate the impact of climate change uh, on the stream runoff. So before going into the stream runoff, we must understand what will happen to the snow and glaciers in this basin if there is a 1 degree rise in temperature. So we will look into that. The first let us look into what will happen if there is uh, 1 degree rise snow cover due to rise in temperature. So what is the idea in this is you have now, now in this figure, you can say the snow cover area in uh, uh, area in square kilometer, and it is altitude. Mm. So what essentially you can see here is that you have this is a altitude versus snow cover area is graph is given. So you can see that this is how. Uh, so what is the idea is this is a graph which is of snow cover, which is as of now. You can see this graph that is representing the area altitude distribution of snow cover in a in a basin, which is a small basin. I think this basin you can check into the paper, and this is Vangargarh basin in Himachal Pradesh. And then what will happen is, as there is 1 degree rise in temperature, that means if you presume the idea that the snow line is representing the 0 degree isotherm, that means you can add the lapse rate and there will be increase in temperature. As there is a 1 degree increase in temperature, there will be increase in snow line. So you can add on the snow line this lapse rate, and you can estimate what will be the future future snow line. Um, so you can add into it and draw the future snow line, and then you can make it graph. So you will know that what will be the new snow line due to rise in temperature. That is a just lapse rate you have. Now, key question is what will happen to the rise in temperature due to glacier AR due to rise in temperature 1 degree Celsius. So what is, so this is the areal extent of glaciers, and you can see that, and that is the area altitude distribution of glaciers. And the pink, what you see here, is a current snow line at the end of summer. What it means is this region is AR and this region is a AR and this region is a ablation area. So, um, so you add again lapse rate to it and get into the new AR. So the AR will change 0.37 to 0.17 due to 1 degree rise in temperature. So what will happen is you will have a new AR and you will have a new mass balance to do that. Once you have a new mass balance, you can estimate the glacial retreat. And this model is used originally developed by Nye in his classical paper in 1960, 1960s paper. If you critically look into that, this gives this model, the net change in a, and this you can also see in Coffey and Patterson's 2010, or there is a subsequent edition is also there. So what essentially you are trying to say here is that how the glacier length will change as a response to change in a mass balance. This is this equation it says. So L1, this L1 is nothing but the net change in a glacier length. B1, what is this one? Is a B1 is a spatially average mass balance. A0, remember this A0 is a ablation rate at the terminus. That means what is the ablation rate of the terminus? And Y mean is a response time and YT is a width of terminus. So this is an LO. So there are two critical parameters in this. One parameter, what is LO? LO is a length of glacier in datum state. So what is the meaning of the datum state? It is very crucial for us to understand. So datum state is a is a imaginary state of glacier where for a given mass balance, glaciers will attain a certain position which will they neither increase or not decrease. But it's really not possible in current scenario, but it is generally taken as a present position. But in theory, datum position is the imaginary state of a glacier where a mass balance remains constant for very long period, and response to that glacier get adjusted in a position where it will neither advance or it will neither retreat. Such is a datum state. So, and then there's another crucial parameter is a T uh, is a is nothing but the other is the ablation rate of terminus. You should know how much is the rate of glaciers at terminus. You can have a mass balance in different altitude or a average mass balance for entire glacier, but what is the melt at terminus you need to know. And this change in glacier terminus, which is going to take place, will take place with the time, which is a TR. And TR is nothing but the response time. So the current mass balance says that if you solve this equation, if you say that glacier, with this mass balance, glacier will retreat by 10 meters, but its response will take place at TR time. And TR means a response time where it is H maximum. That means maximum ice thickness divided by ablation rate of terminus. That is the response time. So many of us, when we were talking about if glaciers have, say, 1,000 meters as a thickness, mean thickness, maximum thickness, and A0 is 1 meter. So whatever mass balance is going to take place now, it will be reflected in retreat by after 1,000 years. That is the idea. So that is the concept of response time. So if you apply this logic, the smaller glaciers will have, if they are located in lower altitude, that means small glaciers will have small maximum thickness and they will have a maximum melt at terminus. Therefore, it will have a response time which is very short. On top of that, big glaciers will have a response time which is very large. If we apply this principle to glaciers which are debris cover, then what really happens is debris cover is a maximum at terminus, and because of that E0 is very low. So for any given glacier, any given altitude, or at any place, if glacier terminus covered by a high debris, then it will be response time will also be longer. That means it will be reflected into the retreat. So that is the idea. And you can solve this equation, and that is one example is given here, but you can also look into the more detail in that paper and say how it will change in winter. So 2004 or 2040 is 209, summer 117 to 111. So you can keep on calculating all this. Then you can also have temperature index, how it is going to change, and how average snow line will change, how glacial extent will change. All those things you can do it, and you can this is what was done there, and you can get how it will change. So you can see here is that maximum will be reduction into the autumn, winter will be 18, summer will be 8%, and monsoon will be around 28%. This is very important to understand, and you see such models help you to understand the processes which is taking place inside the natural. So if you really look into this thing, there is no, if you look critically read that paper and if you understand it, you will realize that in this model we have not reduced the precipitation, particularly monsoon precipitation. But even then, monsoon runoff has significantly reduced, clearly suggesting that as snowfall, um, uh, uh, because that means in monsoon time you have significant amount of runoff is coming due to glacier melt also. As there is a significant, and by monsoon arrives in this valley by July, there is a significant amount of snow cover remains, and as there is rain occurs on it, this really melts very fast. So there is a significant contribution in monsoon time, which is going to come because of the snow melt has significantly reduced. So you can really tell you more about the processes. You can also use the similar idea in a very recently, which is, you can download this paper also. It is a freely available. This work done by Tejal, and you can see here where you can use the WEAP model. So to do it, what is the concept? Is in any models which were used in hydrological purpose, and particularly WEAP model, uh, or some other models where the cryosphere is not very aggressively represented or going into the input, people essentially use the freezing temperature as a criteria. That means for a, you give a temperature and precipitation of a station, then this model will calculate a temperature in various altitude, whatever altitude zones you are given into it. And if the temperature is below freezing, then all precipitation in that region is considered as a snow. So there is no provision in some of these models to provide input of seasonal snow cover, but you have a provision of giving temperature, and then it calculates the snow cover by using freezing temperature. So this is the same idea which I was talking to earlier, because earlier I was talking you about what is articulated in that paper is about if it is a 0 degree isotherm. So it is indeed the same idea used in this model. And then you try to say under different RCP, we will look into the RCP subsequently in the next couple of slides. But here you can see that how glaciers will lose mass by 2050 and disappear entirely by 2090. She in that paper says, and what you can see that how this snow cover will change from various scenarios, and you can see here how it will change 2090, 2050, and as of now 2000 under RCP 4.5 and 8.5. So you look into the 8.5, there is a significant reduction. This is at time versus snow cover area. You can see the significant reduction in snow cover is going to take place. And as a result of that, as there is a significant reduction in snow cover is going to take place, as a result of that, the model can provide you various, like a base flow, rainfall, how much is the contribution coming from base flow, coming from rainfall runoff, coming from ice melt, and coming from snow melt. So you can see how it is going to change over a period of time, and that also can be done by by using the model technique. And you can also use model to understand what will be the small hydropower plants, how this is going to affect the power generation. If you have what will be the when you have a low flow and high head, how much will be power it will generate, or whether there is a change in seasonality of water availability, whether power plant can take benefit of that or not. So some power plant can take, some may not take. So all those issues you can address. But there is also different methods by which you can estimate how glaciers will going to change in future. We have seen the one method where you can estimate the length. We will, but what are the lacuna in in that methodology? If you go into this method and you try to understand what is when we are keeping here, as we change the accumulation area ratio, how in this mass balance, how change in area, what you are indeed going to get is change in length. You may not get the change in area. And some of the ideas we will try to look into how we can go further. So let us now move a little bit further. That means we have now come to the around decade earlier than today, and then we are now have semi-5 model, and there people have used ensemble mean temperature rise into the Himalaya. So how much temperature rise will take place depending upon which scenarios you can use. You can use either RCP 8.5, RCP 6, RCP 4.5, and RCP 2.6. So what it means is that RCP 8.5 is an extreme case scenario. That means the temperature rise by 2030 will be around 2.5, then 2060 is 4.1 and 5.89 by the end of century. So it is an extreme case scenario. And RCP 2.6 is a very optimistic scenario. That means 2.1, 2.34, and 2.27. So what you can see here is that there is no significant change in temperature rise, whichever scenario you would use by 2030, except 2.1 to 2.51. But as you move into 2060s and 2080s, there is a significant change in scenario will take place. That is what, as more and more carbon dioxide gets accumulated in atmosphere, there is going to be change. So that was predicted. This is with reference to pre-industrial period for 1861 to 1990. And this one was predicted in last IPCC report by which this data is done. So first thing we need to understand, if we want to know how Himalayan glaciers are going to respond to those temperature and precipitation changes. Remember, I have not shown you, and I probably missed the precipitation graph, but precipitation is going to increase in this region. So the slight increase in precipitation and increase in temperature, how it is going to change. So this work was done by Chaturvedi et al. And published in 2013 in Climatic Change. You can also download and critically look into how this was done. So one thing I wanted to bring to your notice is look into this elevation versus area graph. So you see this is for all glaciers in the Himalayas, particularly Eastern Himalaya, Central Himalaya, Western Himalaya, and Karakoram. So you can look into that Eastern Himalaya, you can see this is the peak of area under the glacier. That means this is giving the area altitude distribution of glacier. And wherever my cursor is there, this is in Eastern Himalaya. And this is in Central Himalaya, this is in Western Himalaya. But you can see the peak, which is slightly higher in a Karakoram region. This is very important for to understand that and these ranges are very large. It is almost This is from 2,500 or 2,000 to 7,000 meters or 8,000 is topmost. So you can see that around 400, 500 meters, the maximum glaciers are little bit, upward, located in higher altitude in Karakoram. So what it really means, you can look into that. Is there any next slide? Let me see. So what is going to happen is how ELA, you can see here, is as of now. So the data is taken from various literature and say that how much ELA in a Karakoram, in a Western Himalaya, Central Himalaya, and Eastern Himalaya. So you can see here that year 2000, um, this it is slightly lower than, uh, which is a slightly lower than 5,500 meters. It is around 5,000. So in a Karakoram we are talking, and the same area, if we see here, that it is Western Himalaya is really at this at the peak of area, and Eastern Himalaya it is a significantly gone up. That means glaciers are maximum glacier area is below, slightly below 5,500 meter, but your ELA is much higher than this. And that is true in Central Himalaya. So Eastern Himalaya and Central Himalaya now have a situation where these glaciers are going to lose its mass is much higher less. It is slightly better in Western Himalaya and uh, significantly better in Karakoram. So if you look into that, is the precisely why you have as of now the Karakoram anomaly, because equilibrium line is slightly below than the maximum aerial extent of the glacier or altitude of maximum aerial extent of glacier. But as time progresses, and by 2050 or 2080, if you come to 2080, in between 2050 and 2080, this Karakoram anomaly is completely going to vanish. And glaciers will start retreating. Right now, they are stable. Some which are located very high altitude are advancing, but this luxury is going to go in between 2050 and 2080. So now, if we go back to the previous slide and try to understand how we can estimate the future change in mass balance and try and accommodate increase in precipitation into that. This is what you can critically go through go through that paper to understand it better. But you can look into. I can explain it to you. So this technique, accumulation area ratio technique, has been used, and you know that accumulation area technique is in this technique we have correlated mass balance with AR, and that regression relationship is used to do that. Now, what you can do here is, this is a ideal condition. This is a glacier. You can see here, this is the glacier, correct? And now we have altitude of ELA. So this is a current ELA. mm, This is a current ELA, and you can now add 140 meters per degree rise in temperature. That is delta ELA. So it depends upon 2050, 2080, 2090, or 2030, 50, 60, or 80. How much rise in temperature will take place under different scenarios of climate change. So you increase the ELA by using 140 meter per 1 degree Celsius. You can argue that whether it should be 150, 160, 120 is a different ball game. And then you can get the new ELA. Once you have a new ELA under the climate change scenario. So here it is saying ELA under climate change. So what essentially you do is you get the that equation where delta B, AB is AAR into AR under climate change and delta P and BCC. So what essentially you are trying to do here is use this equation with new AR and get the mass balance. Then you say, with the presumption that the physical basis of this understanding is that whatever additional snowfall has taken place, that has taken place or that has remained at the end of year only in accumulation area. So that delta P, you multiply it by, uh, by the accumulation area and then add that into the mass balance and you get the mass balance under climate change. This methodology was used by Chaturvedi et al. And that paper was published in Climatic Change. This has the two fundamental limitations, this methodology. First is this change in precipitation is adjusted with considering accumulation area. But remember, and that is entire precipitation is taken into the mass balance, added into the mass balance. That means it is a less negative mass balance. But remember one thing, some of that might have melted in summer. So there was no way at that time to address this issue. Therefore, it is there. Second thing is there will be change in glacier area as we move from 2030 to 2060 and 2080. There will be a change in area. And that due to change in area, there will be a change in mass balance. And that is not accounted into this method. But this was indeed a first method, and whatever is available data from there, this has been done. And you can see they brought in very interesting results. And this result has probably first time explained Karakoram anomaly very clearly. That means you can see here is this is a Karakoram area for which mass balance is estimated, and you can see here by simply explaining accumulation area ratio and ELA, you can explain Karakoram anomaly, and as of now, or you can see it is at very stable condition. They have slightly positive mass balance. Most of the glacier, Karakoram glacier year 2000 has a positive mass balance. You can see here it is very clearly. And as it moves, it will, depending upon which scenario, RCP 2.6 and RCP 8.6, you can see that how it is going to get collapsed. If it is RCP 8.5, then even by year 2030, glaciers might start losing mass higher rate, and by 2050, substantially loss will be there. And between 2050 and 2080, there is substantial loss will take place. But if you use RCP 2.6, then the glaciers will stabilize by 2050, and there is no significant change in 2030. But remember, this, even though this is very interesting finding, and it has provided a certain explanation for Karakoram anomaly, but remember this mass loss is, we have to account for change in glacier area. That means if we go by 2.5, in my assessment, glaciers might stabilize much earlier than 2050, or much earlier than that, because the glaciers will shed certain area from ablation area, and its AR will become much healthy than what is projected in this, and glaciers will really stabilize. But situation is definitely hopeless in eastern Himalayas. No matter what you do, these glaciers are heading for the finish. Western Himalaya, it's quite possible that in Western Himalaya, you might be able to stabilize glaciers if we follow RCP 2.65, and Central Himalaya will also have, it's slightly better than Eastern Himalaya, but glaciers will have substantially reduced area. So this will be fate of glaciers by middle of century and end of century if we apply this model on a broader scale. But over a period of time, what has happened is there's a change in modeling techniques have taken place, and there is a change in the way we assess the mass balance is also changed. So you have seen this slide, and you have estimated the future projection, mass balance, and area retreat. So this is how you use um, uh, a very different idea where even though eventually you are using uh, uh, AR technique to estimate the mass balance, but you are using um, now the temperature index model to understand mm, the uh, uh, the mass loss. So you have future climate models with, you can take any with extreme climate projection, whichever projection you want to take. Then you take the temperature and precipitation, you estimate the change factor and apply it to the field data. This change factor you estimate by climate model, apply that change factor to the field data, and you get the temperature and snowfall changes. Then by using mass balance model, which you have talked about, and AR, you estimate the improved AR method, you estimate the mass balance, and you can, that is, you get the mass balance for future. Then you can do is, you can estimate the volume of glacier store water, uh, and what you can see is you can estimate the volume loss by glacier mass balance. So, and then you can use the scaling method, and by using that scaling method, you can estimate the future retreat. So equations are given there. You can read critically paper by Veena and Pradeep's paper to understand what it, how it is done, and you can see the volume loss is surface because it is an iterative procedure. So you iterate it couple of times unless such time the solution becomes stable. So your area loss, surface area, the surface mass balance, and number of years you can give, and volume in next time frame, and the area loss in next time frame. You can really do it. You can also estimate the length change also, but there is a slight change in methodology. You can see over a period of time, and people have done it. You can apply this to get the result and how much it will change in future. That means if you take in a Satluj basin, that 50, this is in case of RCP 8.5 scenario, you see. So that is extreme case scenario. The 55% glaciers will disappear, and by end of century, 97% of glacier disappear. How much it will reduce the uh, glacier contribution into the runoff of Satluj also you can calculate. You can go into the paper of Veena and Pradeep to understand how this is done in more result. You can see that how mass loss will change is given here in Satluj Basin. If you depending upon two models, GFDL CM3 under RCP 8.5 and CNRM CM5. So how mass loss will change is projected here in this graph. So, but it is not necessary that glaciers are going to respond to only temperature and precipitation. Uh, that is one way, classical way of looking at it, but things can happen in, there are some other ways, because fate of the glaciers will not only decided by change in temperature and precipitation. It is quite possible change in temperature and precipitation will be driving forces, but there will be a significant change. Feedback mechanism will take place locally. So you can see here is this work is done at IIT Bombay by Gulab Singh and his team. you can see this is a Barashigiri glaciers where you have used um, interferometric technique to understand the velocity and change in elevation. So you can see here the certain region in Barashigiri glaciers, there is a significant reduction in thickness is taking place. And why that is thickness, significant reduction in thickness taking place, essentially because on the glacier there is a, as the debris accumulate on the certain parts of glaciers, there will be some creating uneven surfaces because of differential melting, and that uneven surfaces makes the large number of water bodies on the glaciers. And the water bodies has a significant low albedo, and they absorb a lot of incoming radiation, and you can see that certain region or certain area is of glaciers have abnormally high mass loss. There is also another paper by him for which I have not figured, but what you can see is there are many tributary glaciers are coming into the glacier. As glaciers start retreating, these tributary glaciers will retreat backward, and they will not contribute ice into the glacier, but they will contribute melt water into it. And whenever that melt water enter into the glaciers, there will be hot spot and there is a significant melt will take place. So all these processes are going to increase the glacier mass loss. So it is not necessary that we can use the classical way of explaining glacier mass loss. There will be a significant other contribution, feedback mechanisms are going to take place. And another significant feedback mechanism is going to come because of the debris cover. Even though we know that, as in seen in earlier some of my argument, that if there is a debris cover at terminus, there will be a less melt at terminus and essentially increasing its response time. But as the larger and larger area of glaciers covered by debris, then there is a small ice, water ponds will start forming, and over a period of time, these ponds will become larger, and eventually it will become a big glacier, big lake, and big water body. So when it becomes a big water body, the interaction between the uh, uh, mass loss or glacier change in area not only depends upon the parameters which we had known, it can be significantly affected and we don't know that. So as climate changing and warming is going to take place, the large area uh, glaciers are going to retreat, and as more and more glaciers are retreating, there will be large number of lakes will be formed. And you can see these are the predictions which suggest that how significant number of total, you can have almost 25,000 lakes will be formed into entire Himalayan glacier. So what kind of new mechanism it will bring? So you can see here that just look into this figure, uh, you can look into that how moraine, uh, how moraine
Sir,
dam lake.
excuse me, sir.
Huh?
Sir, your voice is suddenly some problem. It is there. Very feeble voice now.
Now very feeble.
Yeah.
I don't. 1 minute.
Yes, sir.
Let me see now what happened. Is it okay now?
Still
There's a
like,
noise.
yes, and now it is fine.
Huh?
Yeah, now
Now it is.
I think it is.
You can mute others because there is a noise coming from somebody else's. Huh?
Okay, I think everybody is muted. Let me see.
Sure. Everybody should mute. Is it okay? Is it now okay, Arya? My voice is
Yes, sir.
there.
Yes, sir. Now it is fine. Yes.
Okay, so this is the work which is done in. Okay, thank Ankita. So, so influence of what is going to happen is this is the work which is done in Sikkim by Smriti Basnet, and you can see here is how this moraine, if there is a presence of lake, if glaciers are associated with lake, how much it can contribute into the melt. So you can see that how much is so this is a 15 glaciers with number of lakes, and glaciers with lakes are 7, and the contribution of lake expansion is retreat is 64%. That means there is a significant, so all your modeling ideas can significantly change um, once the lakes are formed. Either these lakes formed near the terminus, or these lakes are formed on the small ponds which are formed on the glaciers, or there is a significant amount of water coming from uh, tributary glaciers. So all these things are going to change the fate of Himalayan glaciers much more dramatically than what climate models and what the current methods of estimating glacial change is going to suggest you. Uh, Essentially, in other words, it means the present methodology or present modeling techniques which we are adopting are not capable of addressing these issues of feedback mechanism. We should keep that in mind. So that is the idea on which new research can take place. There is also major issue is going to take place because of the forest fire. As climate becomes warmer and warmer, as seasonal snow melts in middle of winter itself, you are going to get very long period of forest fire. This photograph was taken by me at the beginning of this month and end of last month. That means in month of March and April, now you have huge forest fire into the Himalayas. So this can continue from April, May, June. So you have forest fire period much more bigger now. And as forest fire takes place, there is going to be significant amount of this um, uh, uh, black carbon is going to get transported as it happens in very high altitude onto the seasonal snow or onto the glaciers, and that can significantly change the melting pattern into the Himalaya. So you can see here, this is influencing not only the albedo of snow, but there is some spring over there. Seems to be, it is not visible in shadows, tree shadows, but there is a small spring there. So such spring can be significantly get influence in future. You can see also this is a small spring and water requirement for the. So all those things are going to change in future, and it has already started to change into the mountain. And I have talked earlier about this ice stupa idea, which has been now extensively used in Ladakh. So with this, I think with these words, I would like to stop here and take if there are any questions.